Hello everyone, and welcome to this session on. Oops, where do I have? Okay. Welcome to this session on semaphore and Merkle proofs. So today we have Vivian with us, who's going to be speaking in today's session. Vivian is a software engineer, and she works with the scaling and exploration team with the Ethereum Foundation, and of course she is contributed to Semaphore, still continuing on it, I believe. So, as a part of our ZK month, we have had several sessions, uh, and our agenda is mainly around making people more aware of how to build in the ZK space. We have seen a lot of people wanting to build in the space, but the idea for the entire ZK month is to make sure that we are showing you the practicality of how to do it. And the different topics that we plan to cover throughout this month is basically a cryptography refresher and concepts around that, which we have already covered earlier. Introduction to zero knowledge proofs, we already covered that. We had a session on CIRCOM as well that we have covered. And we'll be covering protocols like snarks and starks and how to build using these. Right now, we are in the snark section. So we covered CIRCOM, and today we are going to cover Merkle proofs, which I believe is a more broader concept, not just restricted to snarks, but CIRCOM uses snarks, if I'm right. And Vivian is the right person to explain more about that. We will also have a Starks week where we'll talk about how Starks work and what are some of the different protocols that are using that algorithm. And then we will also bring in a few different protocols who are working in the ZK space. What are the use cases that they are working on, and how are they using this technology, zero knowledge proofs, to build stuff in the space? Quickly about the Phoenix Guild. Phoenix Guild is an organization that is aimed to get more people, get more diversity in the Web3 space in general. How do we do that? Is by doing education and mentorship programs like this one, where we are providing you with knowledge that you can use to build applications, creating inclusive events, IRL events such as hacker houses, hackathons, and we have different regional hubs across the globe where there are directors who can get trained from us, and then they can teach these sessions and take these sessions for their own regional hubs. And then we have different opportunities, learning opportunities, paid opportunities to teach at as different programs, and some scholarship recommendation opportunities, etc. Of course, we also have jobs that keep popping up on our group, and we are happy to recommend you if you have been a part of any of our cohorts. Our mission is to create and onboard the next million diverse builders in Web3. And our vision is to see a lot of different types of people, diverse people represented in very senior leadership positions in the Web3 space. Here are a few of our partners, protocols, people that we have worked with, and we continue working with the different programs as well as we go. We are a chain agnostic organization, but we largely focus on working with partners in the Ethereum space because it is, of course, one of the more popular ones. And yeah, you can join our community by being a part of our Telegram group, which is a global Telegram group. Follow us on Twitter, give a shout out to the events that we're doing. And last but not the least, I have a request that every time you attend any of our sessions, we all of the speakers who are coming to us and doing these sessions are actually doing it pro bono. What that means is they are giving us 1 hour of their time doing the session and also pre-prepping for the session, right? So the least you can do is give them a shout out on Twitter, give them a shout out on LinkedIn, take a snapshot of the session if you're attending. If you're watching the recording, take a snapshot of it, post it on social media, and let them know that that their time was valuable. You attended the session, you enjoyed this session, and maybe 1 or 2 lines about what you learned, right? Most important is if you write stuff that you learned from the session, it's a really huge inspiration for the speaker to be able to go out and do more of these. So yeah, and I want to thank Vivian for her time today. She is taken out. I'm sure being a part of the exploration team is a lot of work. So thank you so much for taking out your time and doing this session for us, Vivian. Over to you.
Thank you so much. Thank you so much for inviting me. And yes, let's start. I will share my screen. Hello, everyone. My name is Vivian Placencia, and I'm a software engineer in the Privacy and Scale Inspiration team at the Ethereum Foundation. And this presentation, I will talk about the Semaphore. And yeah, let's start. So this is the structure of the presentation. I will talk about what is Semaphore, also identities, groups, and CK proofs in Semaphore. Also, I will talk about Merkle trees and incremental Merkle trees, and which is what we are using in Semaphore, and how to integrate Semaphore into your project, then the architecture of a Semaphore decentralized application, and off-chain application. Too, because Semaphore can be used in both ways. And also I will talk about some use cases and also show some code. And then I will talk about a little bit about the next major Semaphore version, which is version 4. And so yeah, we have time for all these topics. So let's start with what is Semaphore. So Semaphore is a shared knowledge protocol that allows users to prove their membership in a group and send signals such as votes, feedback, or any text messages without revealing the user's identity. And this means that signals have no connection to the identities, and it also provides a mechanism to prevent double signaling. I will talk a little bit more about it later. And Semaphore is a public good project, it's free and open source. Everyone can use it and contribute to it. So yeah, feel free to do it. So since I know that in previous session you were talking about Circum, so I added the tech stack for Semaphore. So we are using the CK technology part. We are using Circum and Snark.js. Circum in circuits and Snark.js to generate the proof, to verify it, and also to generate the solidity verifier. And the proving system we are using right now is a graph system, and we will use the same tech stack for Semaphore version 4 too. Let's talk about the identities in Semaphore. So the Semaphore identities are made up of 2 secret values, a trapdoor and nullifier, and the hash of these 2 values is the identity secret, and the hash of this identity secret is the identity commitment, and the identity commitment is a public value. And this is the way you could create a Semaphore identity. You can create a random identity and also a deterministic identity using a secret message as a parameter to generate the identity. And with this secret message, you will be able to recreate the same identity. And that's this is the way to export your identity. Let's talk about groups in Semaphore. Groups are like sets of individuals, and Semaphore groups are binary Merkle trees in which the leaves are identity commitments, and all the other nodes in the tree are hashes of their 2 shared nodes. So I will talk about Merkle trees a little bit more later, but Semaphore groups are binary Merkle trees. So I added the link to the documentation for identity groups and everything here too, so you can take a look later. So Semaphore groups can be created off-chain with the JavaScript library and also on-chain with the Semaphore contract. So this is the way to create off-chain, and this is the way to create it on-chain. And yeah, I will show more code about it later too. So let's talk about secret proofs now. After you create an identity and you join a group, users can anonymously prove that they are members of that group and send signals such as votes, feedback, or any message. To generate a valid proof, you also need an external nullifier, which can be used to prevent double signaling. So if you use the same external nullifier, you will not be able to verify the same proof twice if you from the same identity. And if you use a different external nullifier, you can send different. You can verify several times the same proof.
Hi, Vivian. Quick question, sorry. Could you go back a little bit and then just elaborate a little bit on what the trapdoor nullifier and identity means? Like in what format? Yeah, this one. So what does it look like, and what is the idea behind this? Like, what is an identity? What do these things look like?
Yeah, I will show more code later. Yeah, I'm explaining like the main concepts so people can understand something about it and get the idea. And I will show more code later, so you can ask me these questions when I'm in the repo. I can go to the code, and yeah, I will show code for people to understand how they can create an identity, and that and also you will be able to see these values.
Sure. Okay, please go ahead.
Okay, I think I was here. Okay, and this is the way to create a proof and to generate and verify. So the zero knowledge proof can be generated off-chain and with a JavaScript library, and they can be verified both on-chain or off-chain. If you verify it on-chain, everyone will be able to see that it's correct. And if you verify it off-chain, you only see that only the server can see that it is correct. And this is the way you can do it for off-chain and on-chain. Let's talk a little bit about Merkle trees. Merkle trees, it is a tree in which every leaf is a hash, and every node that is not a leaf is the hash of its child node. So I will show a diagram so people can understand more about it. It's a data structure used to represent the integrity of data. For example, you could represent the integrity of data if you hash an entire array, but you will see that this is a better solution since you will need all of the elements in the array to get the representation of the data. And with the Merkle tree, you only need some nodes, not all the member nodes. And a binary Merkle tree is a Merkle tree in which each node has at most two child nodes. They are called left child and right child. This is what a Merkle tree looks like. So it has the leaves, in this case L0, L1, L2, and L3, and H0, H1, and H2 are the hashes of the child nodes, and the one at the top is called the root, which is the representation of all the leaves. I will also share this presentation in the Twitter as an answer in the Twitter announcement, so people can take a look at the presentation more in depth and read more about it later. And an incremental Merkle tree is a Merkle tree that is designed to be updated efficiently. So it is used in contexts where data can change over time. So if you need to add new leaves, you need to remove, you need to update. So that's you will need an incremental Merkle tree. And Semaphore is using incremental Merkle trees to manage everything related to groups. So if you want to prove that, for example, here L1 is in the tree, so you will only need to know to prove that L0, H1, and L4. So here, these three nodes, you don't need all the other nodes, and because you will be able to get the fruit, which is the representation of the entire list of members, in this case, the leaves. So that's the good part of the Merkle trees. So I will talk a little bit about how we do this, I mean, insertion and also update and delete in the new version of in the new incremental Merkle tree we will have for the next version, which is an optimized one of the one we have right now. And here we will insert L5 here in this Merkle tree. We will insert L5. So the way we do that, we add this new leaf, and then we hash the last hash here is H3. So then we will name this H4 and then H5 for the others. And we create a new hash which will be the hash of the sibling. This case, L5 will be L4, so the hash of these two nodes. And then since H4 doesn't have a sibling, so we will use this as a parent node too. And then since H4 has this sibling, for in this level, we get the H5, which is the roots. There are several ways to implement the same thing, so this is one of the examples. The idea is to get the same algorithm, but to implement the same algorithm, but you can implement it in several ways. In this case, to update L2 with L5 in this incremental Merkle tree, so here we have L2, so what we would need to do, we don't need the other nodes, we only need this. What we will do is to update all the path until the fruit. So in this case, only the parent node is this one, H4. So right now is H1. So this will be another hash, which is the L5 and L3 hash. And then we will update this hash too and this hash too because it changed. To delete, we add a 0 here, and then you will need to do the same as you did when you updated to update all the parent hashes up to the root. So yeah, the same thing. So updating this one and this one. So that's it. This will be like the algorithm. Okay, so the implementation, you can find that implementation in the research repo in the Semaphore organization, and I will show all these links in the end. So to start using Semaphore, there are three ways you can start using Semaphore in your project. You can use the CLI, the boilerplate, and you can also install the packages manually. With the CLI, you can create a new project using this command. You can also, with the CLI, you can also get group data. So if you create a project, there are 3 supported templates. You could do it, I will show you how to do it with the CLI when I show the code. You could use Semaphore create, and then you will get the option to put the name of the app and also to select the template. There are 3 templates right now. Contracts Hardhat, Monorepo Ethers, and Monorepo Subgraph. So all of them are the same app, which is a feedback app, where you can create an identity, join a group, and then send your feedback anonymously. In the case of the contracts part, it only have the contracts, so the others are complete applications with front end, the contracts, and everything. And yeah, and also there are some commands to get group data, like get groups, get group information about the group, and I will show about it later too. We also have a boilerplate. You can fork it or use it as a template to create your project. These are ways to create your project from scratch. And here is the Leaf app. I will show you the Leaf app later too. And yeah, you can use the boilerplate to create your project. And you can also install all the packages manually. Here is the link to all the packages. This you can use it to create a project from scratch, but you can also, if you already have a project and you would like to integrate Semaphore, you can install the packages manually directly. I will talk about the architecture of a Semaphore app. I will start with the centralized app, an on-chain app, and also I will explain how would be what would be the architecture for an off-chain app. And this is the architecture for a Semaphore decentralized application. And here we have the contracts, the on-chain part, we have the contracts, and here we have the off-chain part. In the contracts, we will use the Semaphore contracts, and we will add the logic we want for our application. And these contracts will emit logs, and this is information about your group, and you will need to use that information to generate the proof in the front end later. So here we have the off-chain part, where we have the front end and also something that I will explain now to send transactions. In the front end part, you will need to use the identity package to create the identities, and you will also need the group and data and proof package to generate the proof. And the group package, you will need it to recreate the group because the information is on chain and in the logs, and the data package is what you will use to get this information, this on-chain information. So the proof generation is always off-chain, and in this case, it will be generated here in the front end. Then to send transactions, like sending a feedback or joining a group, you need to use something. In this case, it could be a real layer or a backend. You need this, any of this, because to keep privacy and anonymity, so the users will not send their transactions. And yeah, you can decide so you can use the relayer you want. There are some in the boilerplate we're using the Open Zeppelin one, but you could use others. There is also another one called Gelato, and you can also create your own backend to send transactions. But the idea is that the user shouldn't send their transactions. And yeah, so this will be the architecture of a Semaphore decentralized application. And this is the architecture for a Semaphore off-chain application. Very similar. In this case, the front end will have like the same things. Everything will be, the proof will be generated there too. But in the backend, we will verify the proof. In the Semaphore decentralized application, we verify proof in the contracts, but this time in an off-chain app, we will verify proofs in a backend, and we will also need a database. The backend should get mail requests to get information and send information. In the database, you will have like the members of the groups and also the signals and the information you need for your application, but at least these things. And this is what it looks like, a semaphore off-chain architecture for an application. There are some use cases. So here I will mention two, UniRep, which is for reputation, to prove reputation without revealing the identity, and Bandada, which is an infrastructure to manage groups, and in this case, to manage semaphore groups. And in this link and in these QR codes, you can find a list of projects that are using Semaphore. And so you can read more about it and get more ideas. And yeah, so go there to read more other ideas. So now I will show some code. Okay. I will start with, okay. Wait a minute. This is an example of application in Node.js is to show how you can create identities, and the repo is here. I will open, I forked the repo. I cloned the repo. You can clone the repo too. So I will show you. Can you see my my
Yeah,
terminal?
we see the GitHub, not the terminal, Vivian.
Yeah. Okay. Okay. That.
Now we see your full screen, but not the terminal. I think you have to open the terminal.
Okay. Yeah. Okay.
Yeah.
Let me open.
Yeah. Now you see the terminal.
Everything? Do you see everything?
Yes.
Great.
Yes.
Great. Great. Okay. I will.
Could you
can you
increase
see?
the font? Yeah. Okay. Yeah.
Can you see Visual Studio Code in the terminal here?
Yes, the terminal in VS Code.
Okay, great. Okay, this is the same. I clone this repository, and this is the same thing. I will show you, like here, this is a way to create identities. This is in Node.js. I will show you after this example how the boilerplate, so it will be in a complete application in front. So in this part, you import the identity package, and then this is a way to create a random identity, and this is the way to create a deterministic one. You use the text one here. Some people use a signature, so yeah, you could use something that is unique, and you know that someone will be able to generate it again, but it's not easy to be generated for other people. And then I will show both identities. And okay, so
What's the difference between a random identity and a deterministic identity? Like, where do we
this
use?
message.
Yeah. So where do we use? Is it up to us? Like whatever?
Yes.
Okay.
It depends on your application. And yeah, so this is a trapdoor, is a hash, and this is a nullifier. This is what you asked before, and this is a secret, which is the hash of these two values, and this is the commitment, which is the public value and is the hash of the secret. And as you can see, both are the same, but they are generated. This message and this is very randomly. And this is the way you can create identities in frontend and Node.js and everywhere. So you need this syntaxes. And for groups, I added the same code for identities. So we have members in the group. But for groups, you will need to import the group package. And this is the part when you create a group. So in this case, this is the group ID. You will need an ID, and if we will deploy an application, you need to make sure that if it's on chain, you need to make sure that there are no other groups with the same ID. So you need to have that in mind. You need to check with a CLI. You can do that. You can check if there is another group with the same ID. So yeah, you need to make sure, because you will get an error if you use the same ID of a group that was already created. And so yeah, we have the members. Yeah, we generate some members to add to the group, and the code is commented, so you can read this later with more time. And here we create a group with ID 1, and this is the 3 dots, and with these members. And for example, if I want to see like the size of the group, so we can see like it's 10. Yeah, it's 10. So we have 10 members. So this is a syntaxes to create a group. And also for the proofs, you will need all of them, like the identities and group, and generate and verify proof. In this case, I'm verifying proof in Node.js. So in an app, in a decentralized app, you should generate the proof in the browser, but verify it on chain. And yeah, here we have the same code, the identities. We have this for groups, and then this is the part for the proofs. You will need these artifacts for Node.js. You can get it. I mean, this is a script to get it, to get them all, these two files, and you can use this. This script is in the Semaphore code too, so yeah, you can take it there. So in the browser, you don't need these files. We will do it for you, but in Node.js, you need to download these files. And since this is Node.js, I downloaded the files, and when this is the external nullifier. The external nullifier is to prevent double signaling. If you want to send several signals, you will need to use different external nullifier. And if you want, for example, a voting app, and you want that people vote only once, you will need to use the same external nullifier, which can be the group ID, for example, and so that they don't send several votes, and they will be able to send only one vote. And this is the signal. This is the way you generate the proof. For this identity, we are creating an identity. Since we use the deterministic one, we are creating this identity, and then the group, and then the external nullifier and the signal, and also the artifacts for CK, it's a WASM and the CK file. And this is the way you can verify the proof with the proof and group depth. And yeah, so I will run this, so you can see that the verified proof will return a boolean, so it's true or false. So these scripts, I configured everything here, so you can identities group from this and groups and proofs, so you can take a look at it. This is what I'm doing now. So yeah, it's true because it was generated and verified and everything is okay. And yeah, this is to show like the general picture of everything separately. So yeah, this for Node.js and Semaphore. Let's go to the boilerplate, which is a complete application. This is a complete application front end, and it also has several functions in Next.js. Several functions and Vercel, and it also the contracts. So yeah, you can clone this repo or use it as a template. So I have the repo here.
Sorry, Vivian, there are two questions. If you don't mind, shall I read those? Okay. One is when the secret message can also be the person's key, right? That's the question.
The person's key.
Yeah, I responded saying it can be someone's signature, like sort of key, but a signature that's derived from their key.
Yeah, the secret message, do you mean to generate an identity?
Yeah.
Yeah, it can be something that a user has, but no one else will be able to know it or recreate it, only if they have your. Yeah, the idea is that if you use something that other people can recreate, they can recreate your identity and use it. And so that's why it's important that this secret message should be something that only the user will be able to recreate. For example, a signature that they sign with their wallet, MetaMask wallet. They will only be able to do it if they own their private keys. And so yeah, that's an example of a secret message.
Got it. Yeah.
You could use it depends on your application. You could use any of these.
Yeah, they are like the community member. They also ask, is it like a password? Yeah, like a password. Yeah, like more of a how can you how can you create a password using maybe your MetaMask wallet, which is a signature, like something that's unique to you.
Yes, yes, there is a code for that. You can this is not the boilerplate is not using a signature because it's not using wallets, but there is a way you could do it, and this is in another repo. I can show now. And to create identities. Yeah, this way is what.
Okay, signer or sign message. So they are signing. Okay.
Yeah, they sign a message, and then this is the signature is used to generate the identity. So this is the client app of another project called Bandana that is using Semaphore. Yeah.
Okay, perfect. Okay.
Yeah.
There's one more question. Is there any way to prevent someone in the group already from joining the group again, since we are using Merkle trees?
No, that's something that the developer should do. We are focused on anonymous signaling, but you should know who will be able to join the group. Maybe with an NFT, they should prove that they have this NFT and or something like that. But no, we only we are only focused in the anonymous signaling and identities in this part. So yeah, you need to take care of that. The developers, you need to take care of that.
Okay. Actually, I had answered this question based on something I had read before, but maybe I might be wrong. That once people have joined a group, like a public, our public key gets added to the Merkle tree, is it? Or
A commitment, yeah, a commitment.
a commitment? Okay. So in that case, if I use the same public key to join the group again, then I won't be able to
Mhm.
create that commitment, right?
If you use the,
Like
if
if
you use what?
someone tries to join the group again
Mhm.
with the same
Mhm.
address, then it automatically does not allow us to join, right?
Yeah. You will be able to join the group several times. Yeah. You need to take
Oh,
care of that in the front end, so
okay.
or in other place. So yeah, the developers should know that and should take care of this, not
Okay.
the protocol. That's not part of the protocol.
Okay. Got it.
Yeah, they should manage that.
Okay. There's one last question, which is so signaling is more like performing an action based on your membership of the group.
Mm-hmm. Yes, the idea is that a signal can be a text, a number, or anything that you want to do in a group anonymously. You can know all the people in the group, but the signal is still anonymous. So you know that someone, when someone in the group sent a signal, you know that this signal was sent by someone in the group, but you don't know who sent that. And that's the part. So yeah, it can be a vote for a voting app or a voting proposal. It can be a vote. It can be a message. Yeah, whatever. Yeah.
Okay. And this one is, does that mean that you will require a different nullifier for each action?
If you want, for example, if you have a vote proposal and you want people in the group to vote only once, you will need to use, for example, the group ID as an external nullifier. So it is the same for everyone. So if someone sends a vote, which is a signal, the vote is the signal, and this information will be saved on chain. So when that person tries to generate to send a vote again, they will not be able to verify it because this external nullifier was used by this person. So if you want that people vote several times, you will need to use several different external nullifiers. So for example, a counter like 1, 2, 3, where people can vote several times.
Okay, great. Uh, yeah, that's all the questions for now. Please continue with. Yeah.
Okay. And this is the boilerplate. We is here in the Semaphore Protocol organization on GitHub. And the boilerplate is a complete application, decentralized application, and is, as I said before, is a feedback app where you can create an identity, join a group, and send signals. So I will test this. So you can clone the repo, and then what you will need to do is to copy this environment variable to test it locally and create a .env file and copy the same environment variables, and then install the dependencies, and yeah, uh, and that's it. Then you can run the project. So the steps are here, and I already did that, so we don't have to do it again. And yeah, so I will talk about the files and everything before testing it. So here we have the contracts and the web application. So in the contracts, we have like a contract, a feedback for the feedback app. So we have the group. We are creating a group here, and the function to join a group and the function to send feedback. here we have, we need to verify the proof to send the feedback. And then we also have the web application, and it has, here we create the identities, we recreate the group to generate the proof, and then we send that to the contract. So here we generate the identities. I will show you everything running. We generate, we create the identities here. Here we are saving the identities in the browser, so that's not a good practice, but it's a boilerplate, so you can do other things. And we generate a random identity, and we are saving the identity to recreate it later this way, because you can use this string to recreate the identity. And then for the groups, we have the function to join groups here. To join group, you need to send a transaction. So in this case, we are using, we could use an OpenZeppelin relayer or any other relayer, or you can also use a backend. Here we have a backend to join a group. This will be the backend. It's a serverless function, which is sending the transaction to join a group. And also we have here the proofs. We need to recreate the group. So we get this information here. We need to get information using the data package, because we need to recreate the group to generate the proof. And then this will be the signal where you write. And this is the way you generate the proof. In the front end, you don't need to add any, you don't need the CK or wasn't file here, because we will do that in the package. And then to send the transaction, the same thing. When you send a signal, you can use the real layer or the backend. So this is the serverless function for this case. And yeah, so let's test it so you can. Here is the doing everything, running everything. Okay, I already created an identity before. So yeah, you will generate an identity. This your identity, like private values, and this is the public value. And here we have the identity. This is the identity. So here we have the identity. And then you will be able to join a group. And this is, you are in the group. And then you can send a signal. So this is what you will see. So this is the same as here. There are some people here. You could join a group. And yeah, this is the live demo. The same thing. This is the local, and this is live. It takes more time. And yeah, these are all the text that people have sent to test the application. And yeah, it's the same thing. Yeah, this is the boilerplate. And also something interesting is the CLI. Is the Semaphore organization, the CLI. This is the CLI. You can install the CLI using this command. And these are the commands you can use. I will, okay. Okay, this is a CLI with information, version of what you can do. So you can create a project, get group information. So I will test all these comments so you can see. And I will create a project. So these are the templates. So I will select this one. The templates are the same as in case of the complete applications, the monorepo for ethers and for the subgraph, they are the same as the boilerplate. The only difference is that the boilerplate is using Chakra UI for CSS, and the templates are using CSS by default, so people can use the CSS framework they want. And then, okay, everything is okay. Let's see this is the app we created. So this is what you will get. The same thing as the boilerplate, the same things. And also, you can get through, and you can select, for example, this, and you will get the list of groups, what people created here, and also here, what people, these are the groups that people created, and you can check here if the ID of your group is there, so you can deploy it or not. Your group ID will need to change here or not, because all of them should be different. And there is also a command to get group information. For example, let's say, I don't know, like information for this, the admin, root devs, and the same for members, and the same thing. This is one member, and for proofs, there are no proofs in this group. Let's see if there are groups, proofs. The one proof here. And and you can use that to get information and take a look at group information. So let's continue with the presentation. And I will talk about some things about the new major version. Semaphore right now is the major version is 3, so the next will be 4. And I will say some new features that we implemented. So we always want to get feedback to improve it, and also the data structure and everything. So any ideas, so proving systems, so the tech stack, so everything. So for Semaphore version 4, we will use the same tech stack, and we did some improvements for circuits, for example, variable names. So the external nullifier is difficult for people to understand sometimes because there is an identity nullifier and also an external nullifier. So for version 4, we will call external nullifier as a scope. And for sibling, 3 siblings, and for path indices, 3 indices. So so people can understand more what is going on and why we are using these things in the circuits. Okay. And also, we will have a simplified identity. So right now there are two secret values, like trapdoor and nullifier. So, and then we also have a secret, which is the hash of the identity nullifier and trapdoor. And then we will have the commitment, which is the hash of the secret. So that's version 3. And in version 3, we also have which is the current one. We also have the nullifier hash, which is the external nullifier with the identity nullifier. So for version 4, we changed that. So we will only have one secret value, which will be called identity secret. So no more trapdoor and nullifier. As private values, we will only have one. And then the commitment will be the hash of this identity secret. And for the new version, the nullifier hash will be the hash of the scope and the identity secret. So it's easier to understand now. Here is the link to the repo, so you can take a look at the code, because everything, all the research and everything is open source. And also, we added some syntactic sugar, so it's easier to read, and it has fewer lines of code. So we also have an additional input to have dynamic depth, because the new incremental Merkle tree supports dynamic depth. The one we have right now is a fixed depth, but for the next version will be dynamic. And also we were thinking to add a new, for the next version, like new other circuits that can be used for any CK application, not only with Semaphore, but these are circuits, but also some of them can be used only with Semaphore, but also other can be used with other CK applications. The idea is to have more circuits, because sometimes people build applications with Semaphore and they need privacy for other things, and maybe it's easier if we have these other circuits that can be integrated in CK applications in general, because there is a repo called CKKit, and we have the data structures there and code there, so we will add information there. And so this is a diagram for Semaphore version 3 circuits, and this is a diagram for version 4 circuits. So just to get the idea of the difference, like we have here trapdoor nullifier and the secret, and then the identity commitment. So right now it will be different. I mean, for the next version, it will be different. It will be only the secret and the commitment directly. So yeah, the external nullifier will be scope. So these things I mentioned before. So here are the changes, so you can see them easily. And also we have an optimized Merkle tree. So this one I explained today. This is the new one. This is the first time explaining this new implementation, I mean, this new algorithms for this new data structure, and it is an optimized one. And we have right now an incremental Merkle tree, but the next version will have an optimized implementation and algorithm and everything. So for the next one, no zero hashes. The one that we have right now has zero hashes, and the next one will have dynamic depth, and we will also support batch insertion for JavaScript, and also for contracts. We are implementing the one for contracts. It's already implemented in JavaScript. And also the benchmarks, we have better results for JavaScript and Solidity benchmarks. Contracts, the new data structure is cheaper, and in JavaScript is faster. So yeah, it's better in general. You can take a look at the benchmarks in this repo. There are the benchmarks. There are benchmarks for JavaScript and contracts there. You can take a look at that. And also you can test it because the code is there, and you can run it and see all the benchmarks locally in your computer. So if you want to learn more about Semaphore, you can go to the website, and also you can join the Discord. Here are all the links, and this is the GitHub organization for Semaphore, and also Semaphore is a project inside the Privacy Infinite Versions team. So if you want to know more about the projects in the Privacy Infinite Version team, you can go to the website. You will have more information there, like the Discord, GitHub, and all the projects we have. And there are a lot of projects and related to CK. So yeah, I think it could be nice if you, I mean, maybe it's interesting for you.
Thanks,
And
Vivian. There is a question by
okay.
Ovia, which she raised her hand. Ovia, are you in a position to unmute?
Yeah, hi Vivian.
Hi.
I had a question about, so basically a proof that a member is there in a semaphore group is the hash of that member and hash of all the siblings at all levels, correct?
Is the
Using
has what?
the proof that a member belongs to a semaphore group is the hash of that member along with the hash of all the other levels in the Merkle tree, and then you compare the root, correct?
Yeah,
That's
correct.
basically the proof. So my question is, let's say you generate a proof, and then in an incremental Merkle tree, the Merkle tree has grown. So how will the proof match at a later point of time? Because the proof is already generated at different hashes. If the tree grows and the hashes change, so how does the in incremental tree, how does the proof stay valid?
Yeah, your question is that you have you generate a proof with a specific Merkle tree that this is the group right now, but then someone remove or add, I mean, the group, there is a new member, or a member was removed from the group, and this proof will be verified or not? That's your question?
Yes.
Yeah, great question. So yeah, we have a root history. So what we do is that this proof will be valid for a certain period of time. So it will compare the roots, and if the group changed, it will valid only for a certain period of time. So we have a code here, but yeah, we have a root history.
But we cannot control when the Merkle tree changes, right? We can't control the rate
No,
of
you don't
use the
know
validation
exactly.
time?
Yeah, you don't know when you recreate the group to generate the proof, you have a group, but if it changed, you don't know. So you will need to generate another group, but it's better to use the same proof because you will need to generate a new one. So what we are doing is that if the group change, this root is valid for a certain period of time, so your proof will be valid for a certain period of time. That's what we do.
Okay, so it's better to generate the proof and then verify it immediately and not wait.
Yeah, but things can happen. So yeah, that's the idea. Yeah, but since it can take time to generate the proof, and then the group change, and also when it's sent to the contract, maybe something changed. But yeah, that's not the normal behavior. I mean that's not what happens all the time. So most of the times, and most of the time is it's the normal way when you generate and you verify without any problem. But yeah, that's the way we are solving that part. So we have a root history, and if your root change, you have a time to verify your proofs, where your proof will be valid for that root. Yeah, the code is for there. Yeah, in contracts. Yeah, somewhere there. Root history. Yeah, we have. Yeah, this part. This is what you mean. Yeah, this part is all here. Mhm.
Thanks,
This
I'll
is the
check
same.
it out.
Yeah, it is what I explained. Yeah. No, I mean it's the same idea what I explained now. Yeah. Yeah, this is the end of the presentation. So yeah, here you can go to the Semaphore Discord and also our website, and or if you have questions, you can ask in the Discord chat or in the PSC Discord too, where there is a chat for Semaphore. Also, you can ask me directly if you prefer. But yeah, um, if you have questions, let us know. Also, if you have ideas for improvements or whatever, or everything is open source. So yeah, if you have ideas to improve the data structure or to change and use another data structure, and yeah, we are open to hear anyone. Yeah, thank you.
Thank you so much, Vivian. This was very insightful. Just as a last question, maybe for everyone who's interested to build stuff using Semaphore, what are some of the use cases that, for example, you would like to get built using Semaphore?
Yeah, here we have a list of yeah, a list of
You shared that there are
projects.
two things,
Yeah,
this
here,
unit. Yeah, okay.
yeah, we have here. There's a list of projects, and there are a lot of different ideas. Semaphore is being used to build identity protocols, also for anonymous signaling, and but we know that there are some use cases that we don't know, but developers can create. So yeah, we want to see like cool ideas and that we haven't seen before, and also real use cases where people can use in real life, because we are trying to create Semaphore in a way that people can use it in their phones and also in computers. So people can create real CK applications where people can use it in real life. So we want to see real world applications. We would like to see like Semaphore in a real world application that people use every day. And yeah, this kind of things.
Awesome. We were thinking of building something very like long before. I think something like whistle blowing might be a good case for actually
Yeah,
Semaphore.
we have like in Semaphore we have for voting and whistleblowing. We have circuits and in contracts. We have extensions. We have one for voting, so
Right.
this will help for people that want to build voting applications, and this for whistleblowing
Okay.
applications. So yeah, I think this can help. Yeah, but this is one use case too. Yeah.
Oh,
And
nice. Yeah, I mean, there are a lot of upcoming hackathons. There's like the ZK stuff. There's a lot of ZK stuff happening in Dev Connect as well. There's the Eat Global Istanbul. So I'm sure for those who are watching this, it's very helpful to just take Semaphore as is. Like there's a lot of boilerplate code, so you can definitely take stuff and build interesting things. Oh, this is a very nice
yeah,
list
yeah,
application.
it's really long. Yeah, I don't know if you do you know about Susalu? The Susalu passport was built using Semaphore,
Oh wow,
and
I've heard of Zalu. I didn't know that they built the passport using Semaphore.
yes,
Very
the Susalu passport. Yeah, and you could do things anonymously with that. And yeah, there are some applications, interesting applications here using Semaphore. And yeah, you can take a look at them and read about them. Yeah.
very cool, very cool. Yeah, thank you so much. Thank you so much, Vivian. Yeah, thanks for your time. We really appreciate it.